Hello everyone, welcome to the fifth session of the quantum field theory. Today we are going to talk about the Dirac equation. Dirac equation is used to explain the behavior of the fermions. So fermions, they are particles, or they are fields that have a spin structure. And by spin structure, we mean some form of a space-time configuration in the field that carries extra information other than what particle was representing in a space-time. So along with the space-time, we have more information on other components of the field. And also fermions have different statistics. So we're going to see how Dirac algebra is going to lead into a form of a statistic that we're calling it Fermi-Dirac statistic, that it is something explicit for fermions that causes fermion to only occupy one particular energy state at the time. So in the bosons, if we have multiple energy states, imagine if we have multiple energy states that I'm labeling them with the epsilon, you can have multiple bosons in one energy structure, and there is nothing really prohibiting that. But for the fermions, that's not the case. So basically, if we have multiple energy structure, we can only have one fermion at a time in each energy state. So that basically means the fermions are distinguishable if they are occupying different energy states. And we're going to see how the Dirac equation is used to explain 1/2 spin structure. Of course, we have different type of spin. We have a spin, more complicated spin structure, more dimension of speed. But as far as we're concerned right now, as far as we know about a standard model of particles, electrons, quarks, leptons, they have a spin 1/2, and that's the minimal spin structures that we can use. Okay, so we're gonna start with the question of what is Dirac field or fermionic field. What is Dirac field? So we previously talked about a scalar field such as Klein-Gordon field, that we were showing it with phi. So this phi of x and t, it doesn't have any component, any extra component, and that is something that makes it a scalar field, which means that if we are changing the coordinate, if we are rotating the space-time, if we are rotating we are boosting the space-time, which is a form of rotation, we are not changing any component of the field, and the field, it remains the same, so as the Lagrangian that we are constructing out of that field remains the same. So now we can move into a more complicated structure that we call it a vector field. A vector field, for example, we are familiar with the electric field, magnetic field in classical electrodynamics, that's something that has component, something that we can label it with the I component. So it depends how many components it has. It depends on the theory, how many dimensions of space-time we have. But in general, a vector field is something more complicated than a scalar field. It has component. And the point is, when we are changing the space-time, when we are rotating the space-time, transforming the space-time, doing a boost, Lorentz, in general, Lorentz transformation, we are changing those coordinates. So the different coordinates of that field are changing with respect to each other in order to keep the Lagrangian still a scalar. So the whole point is that the field is not a scalar. The field is not a scalar by itself. The Lagrangian is still a scalar. I mean, this is something that we are demanding because the physics is encoded in Lagrangian. So Lagrangian should be a scalar. So that's how we can get a vector field and construct a scalar out of it and construct a Lagrangian, which is a scalar. But in general, a vector field has components, and those components are carrying more information about the spacetime. So we are going to see how, in the case of Dirac equation, those components of spacetime are related to spin, or as we are going to discuss, right-handed and left-handedness of those particles, which is somehow related to the direction of the spin with respect to the momentum of the particle. So a vector field is showing with psi. So this psi, we should not make a mistake between the again psi and the wave function in Schrödinger equation. So that psi is something different. So this psi is just representing a vector field, which is representing basically particles that are fermions. So let me write down the Dirac equation. So what was the Klein-Gordon equation? So Klein-Gordon equation was box squared. Sorry, my box is not really good. Yeah, so box squared plus m squared acting on phi is equal to 0. So that's Klein-Gordon equation. So the Dirac equation is different. So we have I, some matrices, gamma mu. So gamma mu has an index, which means that there are multiple matrices, but mu runs from 0 to 1, 2, and 3. So basically we have 3 space and then 1 time component. So we're going to discuss this mu is related to the representation of the Dirac equation in certain particular space-time. So here we have a 4-dimensional space-time. So we're having these 4 components of these Dirac matrices. And then we have the derivative, but the derivative also have the index mu. So we're going to have the matrices and the derivative mixed together. Minus m, or the mass, and then acting on some vector field equal to 0. So that's a definition of Dirac equation. So Dirac equation is a little bit different from Klein-Gordon equation. So Klein-Gordon equation, again, is just simply one scalar field, and this is an operator. Again, that this operator is not like a matrix. It's not multi-component. But in the Dirac equation, this operator is like a matrix. And this psi here is like a vector. So basically, Dirac equation is something like this. An operator acting on a vector is equal to 0. So it's basically multiple equations. It is not only, it's a matrix equation. So when we have a matrix equation, which means we have multiplication of multiplication of the rows and columns, and then each of them are individually equal to 0. So that's why a Dirac equation is more complicated and has multiple components, and each of those components are related to the spin of the particle. Okay, so that's how Dirac equation is something acting on multiple component of the vector field. And there is another difference between the Dirac equation and the Klein-Gordon equation, is that Klein-Gordon equation is the second order differential equation. So as you can see, there are second order derivative present here. But in Dirac equation, we have a first order differential equation. So what is the difference between first order and second order differential equation? we can somehow say something that has first order differential equation is more fundamental than something that has second order differential equation, because anytime we're taking derivative, we are losing some information. So we can show simply that Dirac equation can give us Klein-Gordon equation, which means that we can take another derivative from Dirac equation and just rederive the Klein-Gordon equation. So having the first derivative differential equation is has something more to offer, and that's a fundamental difference between the Dirac equation. And in particular, Dirac was searching for the first order differential equation to explain the behavior of the fermions. So that's a deep discussion. I probably will discuss it more, why Dirac equation have this first order derivative. But in general, in classical physics, when we are talking about waves, if you remember the whole discussion about waves and simple harmonic oscillator. So if you remember, simple harmonic oscillator was x double dot, or second derivative of x, plus some w squared of x is equal to 0. So Klein-Gordon is similar to something that we're calling it simple harmonic oscillator or simple wave. But so that's how probably people were thinking about Klein-Gordon equation sooner than Dirac coming up with his equation, which was first order. So it was really natural to think about a second order differential equation because it's more similar to simple harmonic oscillator. But we're going to show that this first order definition of the Dirac field having some benefits that makes it in particular good to explain the behavior of fermions. Okay, now the goal is to show that the Dirac equation is invariant under general Lorentz transformation. So the point is to show when we are going from x to x prime, so the difference between just labeling them x and x prime is a Lorentz transformation, which we show it with some matrix element of some lambda matrix with two index, mu and nu. So x is equal to, or x prime is equal to lambda. So we have x mu here, so lambda mu, and then nu. The index nu is a free index, so it goes to x prime. So that's the general form of the Lorentz transformation. And we want to show if we do such a transformation, if we're taking x to x prime, then the psi of x is going to be something like a matrix representation, which we show it by S, and that S is living in the same dimensional space as the psi field is living. So this S of lambda, which is a function of that specific Lorentz transformation, let's say, is acting on that psi of x. So psi of x, let's say, is a multi-component field. So we can say psi of x of alpha. So there is some alpha rows in psi of x, psi 0 of x, and to psi n of x. It depends which representation we are showing the psi field or the Dirac field. But that S is also having similar number of columns in one row. So if there is a alpha component here, there is alpha component here for that S of lambda. So S of lambda is the field transformation. So it's a field transformation that rotates the field. I mean, it is like a rotation, it is like a transformation to keep the Dirac Lagrangian, which we show with L, invariant. So in general, when we are going, so imagine that we are just adopting this notation. So x prime is some Lorentz action or Lorentz transformation acting on x coordinate, on x coordinate, and take us to a new set of coordinates. So the way to proceed this is to write down the Dirac equation. So the Dirac equation is, imagine the Dirac equation is correct for some psi of x. Okay, so we are in the x coordinate, and psi of x is the Dirac function, multi-component function that we want to show that is invariant under this transformation. So actually we don't want to show it. We wanna see if we want to keep it invariant, what would be the properties of the matrix S, and what is the relationship in particular with the gamma. So we have psi x, and we have x and psi of x, and then we do the Lorentz transformation. We take it to x prime coordinate, and we are taking into the psi prime of x prime. So psi prime of x prime is equal to S of lambda acting of psi of x. That take us from one coordinate point to the corresponding coordinate point after such a transformation is being found, and we're going to see what would be the properties of this S. So we just want to show, if we are simplifying this transformation by some S matrix, if we imagine there is a 1-by-1 relationship between each Lorentz transformation and some form of representation in the space that psi of x is living in the same dimension, then we're going to find a set of laws that help us to keep this equation invariant. So we basically have the Dirac equation. So let me write it down. I gamma mu d mu minus m acting on psi of x is equal to 0. So this is where we begin with. And then so I'm going to write down the psi of x based on the transformation that we previously wrote down. So psi of x prime is equal to S acting of psi of x. So psi of x is going to be the inverse of this matrix S of some lambda acting on psi prime of x prime. So it is rational to think that for any particular Lorentz transformation, we have also the inverse of that Lorentz transformation. So that mathematical relationship is well defined. So for any particular boost, we have something to cancel it out and take into identity, which means that for any boost, we find the opposite boost, that we are just taken from one coordinate to another coordinate, and then we can go back from that coordinate to our original coordinate. So it is rational to think that this kind of inverses exist, and we can then write down psi of x as the inverse of that matrix acting on psi prime of x prime. So now we need to change this equation and write everything based on x prime, right? So another thing that we need to change is the derivative with respect to mu. So the partial derivative with respect to the muth component of the space is defined as something like this, x mu. So the index is basically up. So when we say x prime is equal to lambda acting on x, basically x is equal to the inverse of that Lorentz transformation acting on x prime. And if we want to do the component, we can have a component here. So we can write down a component. So in general, we can write down x mu as the inverse of this Lorentz transformation acting on x prime of nu. So I'm going to write it down. So I'm going to write down the derivative d mu, and I want to turn everything into some form of d mu prime. derivative with respect to x prime. So I'm gonna write down as derivative as with respect to x mu. So we're basically doing something like that, and then we say x mu is equal to lambda minus 1 mu nu, sorry, lambda minus 1. So we have x nu mu. So we write it down like that. So we conclude from that is that, so the derivative can be written as x nu. So what we're doing is that we are taking this coefficient out. So we're gonna have mu nu derivative with respect to x prime nu. So I can write down this term as d nu prime, and then I have this term behind it. So when we are inversing, we are changing the place of the upper index and the lower index. So we're going to write it down as lambda minus, but we're going to take nu up, and then we're going to take mu down, and this term is just the nu prime. So now this is equal to derivative with respect to the muth component of x coordinate. So now we're going to write down the whole equation. So gamma mu, we have the gamma mu here, and then we have this term here. Minus m s minus of lambda acting on psi prime of x prime is equal to 0. So now what to do with that? So we have this term here, gamma mu. We have to turn it into something that has a nu on it, because we have this d nu prime derivative, and if we want to remake the Dirac equation in the x prime coordinate, we have to take that gamma term with the mu index into something with the index mu. So now this is a place that we are define some properties for those S matrices. So those S representation that acts on the Dirac field should satisfy certain equation to do something with this gamma here. So we are gonna do something right now. We are doing some tricks because we know what we're doing. So I'm going to multiply the two sides of the equation by some S of lambda. So we already have this S minus 1 here. So I'm trying to sandwich it with some S of lambda. So the other side is 0, so it remains 0. That's probably the power of 0 here. So this particular equation is leading us to the following expression. So this S of lambda acting on gamma nu S minus of lambda is equal to the same Dirac matrices of index nu, the lambda, so Lorentz transformation of sigma and mu here. So we have this mu upper index should be the same. So there is this sigma dummy index. So this is a kind of equation. Again, this is a main condition of S matrix. So when the S matrices are acting on the Dirac field of psi, then that they would keep the Lorentz invariant. We would keep the Dirac equation invariant under this particular generalized Lorentz transformation. The question here is how to find S of lambda in, let's say, 4-dimensional representation. So why four-dimensional? Well, basically that four-dimensionality of the Dirac field is related to how can we describe the spin based on left-handed and right-handed. But we're going to see is psi of alpha. Alpha runs from 0 to 1, 2, and 3. So we have 3 space and then 1 time component. But we're going to see that these dimensions are going to group together into 2 different and independent components. And the question is, what is the S of lambda? So this lambda is the Lorentz transformation. This Lorentz transformation can be infinitesimal, so the lambda can be written as the identity plus some infinitesimal omega transformation. We're basically saying lambda mu nu, or any permutation of the index upper and down is equal to I mu nu plus omega mu nu. Or you can even say lambda mu nu is equal to I mu nu plus omega mu nu. And this omega mu nu is equal to lambda mu nu minus I mu nu. Okay, so this is how we can get these omegas. So S of lambda can be written as exponential term of some I. So we have this I complex variables, and then we have the generators of the group, the generators of that representation, which we are going to see how it is connected to the gamma matrices, times the omega, so the infinitesimal angle or infinitesimal parameter for rotation. So in general, this form of transformation can be written as the exponential of some infinitesimal parameter. So here, G, in general, G, or the generator, are they are produced with the gamma matrices, which is the commutation relationship of the gamma. So gamma mu and gamma nu, they make S mu nu. So imagine the commutator of the gamma matrices. And some important properties for those gamma matrices that we have is that the anti-commutator of gamma mu and gamma nu is 2G, or the matrix element, or matrix, the metric matrix. So G is basically the metric, and here we are just basically talking about the Lorentzian metric. So the anti-commutator between gamma and gamma nu is just producing the metric here. So this is what we have. So this is the basic algebra or anti-commutation algebra, and this is something that we define. And we are going to show that the general Lorentz transformation, or the general Lorentz group, they can be explained completely by those S, the commutation of the gamma matrices, because they basically satisfy some properties that we expected from the general Lorentz group. So the exponential term is like this, the exponential of I. So we have S mu nu, and then we have omega mu nu. So that's the representation of some specific particular Lorentz transformation. So as we said again, this omega mu nu is basically lambda mu nu minus I mu nu, and this S is just simply the anti-commutator of gamma mu gamma nu. So the last thing I want to say for this session is that psi of x is not a 4 vector, because a 4 vector kind of should transform under the Lorentz transformation directly. So what's the difference between the spinor and 4-vector is that the spinor uses a representation of the Lorentz transformation, which we already explained. So basically, for example, A mu, if you're thinking about the 4-vector, for example, A mu in electrodynamic, which is the vector potential, transforms like this. So lambda mu nu A nu, or A prime nu. So this is something that we call it a 4-vector. 4-vector have 4 components, and just directly using a Lorentz transformation to transform it. And I think that's a point here, that psi is not a 4-vector. However, this is like a kind of coincidence that psi has 4 components. So I have to kind of correct what I was already saying, is that it is natural to think we have psi 0, psi 1, psi 2, and psi 3. And you think about this psi 0 as the energy component, and look at these 3 other components of the psi, and you think about them as a space component. This is not correct, because psi is not a 4-vector. Psi is a spinor. So I kind of have to correct what I said. The dimensionality of a 4-dimensional spinor and a 4-dimensional 4-vector basically is a coincidence here. But it is a very interesting coincidence, because it shows the compatibility of a space-time, a 4-dimensional space-time, and basically a particle and antiparticle with the opposite spin. So basically, this psi of x is a spinor. And when we say a spinor, which means it transforms under a representation. So this word is very important. Representation of Lorentz transformation, which we already discussed about it, S of lambda. So whatever Lorentz transformation we are using, lambda, but we have this S of lambda, which then S of lambda is infinitesimally expressed as we showed above. It's the exponential term of I over 4. I mean, this 4 is like a convention here, but we have this S of mu nu acting on this angle omega mu nu, which we already explained. Omega mu nu is basically the Lorentz transformation, mu nu minus I mu nu minus identity. So basically omega is a measure of how much we're deviating from the unitary operation or doing nothing. And also this S mu nu, as we explain up here, is the commutator between the gamma mu and gamma nu. And this is a SU2 times SU2 Lorentz transformation, a representation of Lorentz transformation. So in general, let's remember something from quantum mechanics. So for quantum mechanics, when we are talking about the spin, if you had the quantum mechanics course, one of the probably main start point of the quantum mechanics is the concept of a Stern-Gerlach experiment. And in the Stern-Gerlach experiment, you are dealing with the spin and the spin operators and how to express a spin in the internal quantum structures. So basically, the spin is a 3-dimensional structure, but you can encode it in a SU2 group. So if you study a little bit of group theory, in group theory, for example, we have this rotation in the 3 dimensions. So imagine we have this x, y, and z, and you have a vector here, r, and then you can transform this vector by some rotation in the 3-dimensional space. So, for example, r prime is equal to some r, and that's r is like a operator. It is a matrix, or it has a representation acting on r and produces r prime for us. So it's like a rotation, right? So we can basically quantify this rotation here. So let's say using, and this is the angle here. So this angle could be infinitesimal, it can be large, but the point is if this angle is large, then you can think about this rotation as the summation of so many infinitesimal, a small angle rotation. I think that's the whole point of it, that you can turn any particular form of transformation as the summation or the perturbation of a small and a small Lorentz transformation here. So, okay, so the whole point was that if you have this three-dimensional rotation, let's say three-dimensional rotations, you're showing them with the SO3 group. So a special orthogonal three-dimensional groups, they're orthogonal because you can have three independent types of rotation that are independent from each other. I mean, they cannot interfere with each other. So each axis, for example, is one particular way that you can rotate something. And for example, one R can be expressed as Rx, Ry, and Rz of some particular rotation. And the whole point is that, for example, if you make R1 and imagine you make R2, let's say R2 is made of Ry, Rx, and Rz, R1 and R2 are not necessarily commuting with each other. So there are so many examples that you can rotate something in a different order and then the final output is something different. So that's why you're basically seeing that even in the classical work, rotation is an example of how to make a quantum mechanical structure that they do not commute with each other. So in classical physics, most of the things that we do, for example, measuring the momentum and the location, can be simultaneously done, but two rotations with a different order of the axes is not something that we can really make it to be the same outcome. So the rotation is one of the things that doesn't commute, and it's a very good help because SO3 is isomorphic. So the term isomorphic mathematically means that we can find a 1-by-1 function. So there is a function here to take any member of the SO3 rotation group to SU2, or a special unitary group with the trace of 1. So we are basically reducing the dimensionality of SO3 to SU2. So we're basically talking about a real, the real means real number 3D rotation, or real 3D vector. Now we're going to a 2D complex space. So we are basically not losing any information because, again, for the 3D rotation, we need three numbers. When you go to 2D complex numbers, we basically have 2D, but each of them has a complex value. So you might say each complex value is 4, so 2 times 2 is 4. But you also have to remember that the trace of these matrices, a trace of, for example, SU2 matrices is 1. So that is like a constraint that reduces the dimensionality from 4 to 4 minus 1 is 3. So we can simply show that for any SO3, there is an SU2 in a complex space. And this can be done in a spin representation. In the quantum mechanics, very basic quantum mechanics, you can show that the spin is something that satisfies. It's very similar to SO3. So we have these Pauli matrices. So these Pauli matrices that are shown with the sigma or sigma I, they satisfy those algebra which is so similar to SO3. So with those matrices you can simply reproduce the rotation in three-dimensional space, but for the spin in the internal SU2 structure. So sigma 1, if you remember, was 0 0 on the main diagonal, and then 2 1 here. So it's similar to unitary matrix, but it is another diagonal. and sigma 2 is equal to 0, 0 minus I, and that's where the magic of complex number comes in quantum mechanics. So in quantum mechanics, you go from three-dimensional space to something more dense and compact, but you have these complex numbers to help you. So you have 1 and minus 1, 0, 0. So these are like three Pauli matrices that you can use them in order to rotate a spinor. A spinor is a two-dimensional entity. So the spin of something, a spin of one particle, was a two-dimensional entity, S1, S2, and then those Pauli matrices and other transformations in SU2 are acting on them and taking them into S prime 1 and S prime 2. So that's an spinor. So a spinor transforms under a representation of SO3. So now we can see what's the difference between the 4-vector and a spinor. So the Dirac equation is the equation for a spinor, not for a 4-vector. So maybe that's a coincidence that the dimension of a space-time here, 0 to 4, is similar to the dimension of the Dirac spinor. But Dirac spinor is basically 2 by 2 spinor. So now let's go. So now we said for one particular one-dimensional quantum mechanical particle, SO3 can be translated into SU2. Now, for the case of Lorentz transformation in 4-dimensional space-time, which is SO13, so now this 1 stands for time, and this 3 stands for space. So any kind of vector, 4-vector transformation under Lorentz transformation can be mapped into, so there is another, again, function here that you can map it as 2 independent SU2, SU2. So when I'm writing down as a multiplication, there is another way to write it down as SU2 plus SU2, which means that you can really break down a spinor into 2 blocks that are kind of independent from each other. So they are coupled actually to each other, but they can be seen as independent entity. And then you can say that group has 2 subgroups, and these 2 subgroups are spanning the whole group. So how is it going to happen? So let's go back again to Dirac equation. So the Dirac equation is I gamma mu d mu minus m is equals to acting on psi is equal to 0. And so now the question is, so now we know this equation is generally invariant under Lorentz transformation that satisfy this particular relationship here, which is the gamma mu nu lambda mu nu gamma mu. So if we have this particular condition satisfied, any representation of the Lorentz group S that has this characteristic feature then can be used to transform psi. So I mean the whole point is that this S, we have to find something for this S, and this S is a particular representation of the Lorentz group. Now the question is, what is this S? We can basically relate this S to the Pauli matrices very simply because they have a similar algebra, and we are just talking about the spin. So now I'm just bringing out something from my pocket, and I call it like the gamma matrices or Dirac matrices. But Dirac matrices are constructed from the Pauli matrices. So I would say, yeah, such a transformation, such a gamma matrices can be this. So I can just write it down as a 4x4. So this is a 4 column and then 4 rows here. And I can just simply put 2 identity, so one identity and one minus identity on the main diagonal, and I call it gamma 0. And then the gamma I, which means anything other than 0, can be written as 0, 0 on the main diagonal, and then you have sigma I and then minus sigma I. And sigma I are basically Pauli matrices. that we already talked about. So then we have this 2 by 2 block inside of these gamma matrices. And now if I try to write down this Lorentz transformation here, so let's say again, go back to Dirac equation, I gamma mu d mu minus m psi is equal to 0. Now let me just, so this psi was basically psi 0, psi 1, psi 2, and psi 3, and might be a reason we make a mistake between a 4 vector. But basically I need to divide psi into two basic units. So psi 0, psi 1, psi 2, psi 3. And let me call this unit psi L, and let me call this unit psi R. And the letters of L and R stands for left-handed and right-handed. But we are going to talk about why. Maybe now we're just confused what is left-handed and right-handed. But we're going to see by left-handed and right-handed, we means a particular component of the field that has a spin that is in the same direction of the momentum. And there is a component of a spin which is in the opposite direction of the momentum. So basically, right-handed and left-handedness is it's a question of how the spin and the momentum are in the same direction or in the opposite direction. So now if I turn this spinor into this 2 by 2 unit, I'm basically dealing with that. So psi L and psi R is equal to 0. Now, let me write down this operation, which is the main operation, as now I say I. So I have this I beside all of that, minus m of psi L, psi R is equal to 0. But now what do I have? I have this 0, 0, I2 minus I2. Sorry, I made a mistake actually here. So this is off diagonal. So this is minus I2. And this is I2, and it's 0, 0. Sorry, there is no element on the main diagonal components of the gamma 0 matrices. So basically, it is off diagonal. The derivative with respect to time plus 0 sigma I minus sigma I 0 I sigma I of psi L psi right. So now I can just basically write this as one giant matrices that has 0 and 0 on the main diagonal term. And then there is minus I 0 plus sigma I dot sigma I dot, so let me get more space, sigma I dot I, the derivative, the ith derivative of the ith component of the derivative. And on the other hand, I have I0, ID0 plus, minus sigma I dot I sigma I, acting on psi L left, psi R, and then you have minus m. So minus m can be written as minus m, the main two diagonal term here, psi L and psi R is equal to 0. Now the whole thing can be re-expressed as I. So well, I can be cancelled out because we have 0 on the other term, but we have basically this giant matrices minus m, and you have minus I derivative with respect to 0 plus sigma
dot the derivative. So there is this I term here that we can actually take out. So we can take out this I term here. And you have the zero component of the derivative. And then we also can take out this I here from here. And then we have the time derivative minus the inner product of the Pauli matrices in the derivative operators. And you have sigma L and sigma R, psi L and psi R. And then we're going to get something very interesting, is that now we can see that we have two coupled differential equation. So I basically have minus m psi L plus I time derivative of psi R equal to 0. And then I have the next term is I time derivative of psi L minus m psi R is equal to 0. So now we can see how right-handed and left-handed component of this spinor are connected to each other. So they're basically coupled to each other. And that's the properties of mass, that how mass is playing a role between connecting psi R to psi L, right? So this is the mass. So in probably more advanced topics in particle physics, you realize that if you have mass, there is always a transformation that you can turn a right-handed particle into left-handed particle. So basically, if you have a right-handed particle that has the momentum and a spin, so there is always a boost. So if there is always a boost, that you can take a right-handed particle into a left-handed particle. And that's what basically the Higgs do. So the Higgs particles, what they basically do is to stop a left-handed particle and turn them into right-handed particles. And that's the whole point of mass. And that's how mass is like an inertia that makes the right-handedness and left-handedness not as an intrinsic property, but something that can be interchanged. But if the mass is 0, the right-handed and left-handed particles are completely separated with each other. So if the mass is 0, then all I have is to have two independent equations. So I have the Dirac matrices independently for psi R, and then I have the Dirac matrices in a slightly different form. So that's the difference between right-handed and left-handed. There's a plus sign here and there's a minus sign here for the left-handed particle. And that's how right-handedness and left-handedness are separated from each other. If there is no mass, and there is no way that you can take a right-handed particle into a left-handed particle. So that's the case, for example, for the photons or for gluons, particles that you don't have mass, those gauge fields that doesn't have mass. But the rest of the things that we are talking about, for example, the electrons, quark, leptons, or quarks, even neutrinos, they have finite mass. They have even a small mass can make them be coupled to each other. So we basically have a few massless particles. We have photons and then gluons. Even at the high energy, the force carrier for the weak force can be also massless. For example, W boson and Z boson can be massless, but in the certain regime that we are, W boson and Z boson, they are massive, but we have gluons and we have photons. So gluons is basically for SU3 transformation, gauge theory, and then photons for SU1. And these two massless particles, they have a kind of separated chirality, which means a right-handed photon can never turn into a left-handed photon. Right-handed gluon can never turn into the left-handed gluon. And that's kind of the beauty of the Dirac field. And that's how these fermions are separated, and that's how mass is playing a role in creating an inertia in the Lorentz transformation. So I think now we are fine for today. In the next session, we are going to talk about the answers to the Dirac equation, how to solve Dirac equation, and then based on that answers, how to quantize the Dirac equation. And after we quantize the Dirac equation or Dirac field, then we can calculate the propagators and causality and those similar things that we did for the Klein-Gordon field. So after we quantize it, after we learn how to express the operators based on the eigenstates of the energy and momentum, we can calculate the propagators. And then we are ready to link between the Dirac field and also a similar bosonic field and create a theory of interaction. So we are not still in the interaction theory. So we are in the free theories, which means, Dirac equation alone or Klein-Gordon equation alone. They are not connected to anything. They are not coupled to any other types of particles. So we don't really have an interactive picture. So these free theories, so we quantize them. So when we quantize them, then we can make a coupling between those free particles. And then when we couple them, we need to go to the interaction picture. We're going to talk about the interaction. We talk about the interaction picture at the first session of these videos. But we're going to, again, review that and how the interaction picture can be used to calculate the Feynman diagrams. Feynman diagrams are interaction between those free fields plus some perturbative interaction. So for today, what we basically did was to introduce the Dirac equation. So let's do it again. So this Dirac equation was some form of first order differential equation in contrast with the Klein-Gordon equation, which was the second order differential equation. And we talk about the Lorentz transformation. The Lorentz transformation are something that takes any coordinate to another coordinate, and anything that transforms under Lorentz transformation, they're called four vectors. And X, P, even electric field, the vector potential in electric field are basically four vectors. They transforms under Lorentz transformation. But the representation of the Lorentz group, general Lorentz group, is S of lambda. And we try to kind of find the properties for that S or representation in order to keep the Dirac equation invariant. So our whole point was to keep the Dirac equation invariant under a representation of the Lorentz group. And then we found that this particular S should have these properties here. So this is the conditions we derived from the Dirac equation that should satisfy. So it's a connection between the gamma matrices, so these particular gamma matrices, and this representation of the Lorentz transformation. And then we express how to find this representation of the Lorentz group. If you probably were interested to do some complicated algebra, you can basically prove that this S that we constructed from those gamma matrices, they satisfy the relationship that we need for the Lorentz algebra. So we have the generalized Lorentz algebra, and probably we can talk about it in another video about it, but you can just simply prove that this S of lambda that constructed out of these gamma matrices, they are good. They can satisfy certain relationship, and we said that there is a coincidence that this psi has four components, but it is not a four vector. It is a spinor, and a spinor is something that rotates under the representation of the Lorentz group. And we explain how SU2 is connected to SO3 for one particle, and then if we go to Dirac equation, we have SO13, which has time component, which can be corresponded to SU2 times SU2, or two independent SU2 group, which correspond to basically subdividing any spinor into two components, psi L and psi right, left-handed and right-handed. Each of them are 2 by 2 units, and those 2x2 units, they transform under SU2, individual SU2, and then the only thing that couples them is this mass term. So how this mass term is making them interconnected, and then if the mass is 0, we don't we really don't have any connection between the right-handed and left-handed spinors, and that's how they can be separated. However, I have to again remember that gluons and photons, they are not fermions. So the concept that we talk about Dirac field is for fermions, or particles with the spin half structures. So I mean, this argument of chirality or the massless particle is not directly applied to gluons and photons, because they have different equations. They are bosons, and we need to have the gauge equations, gauge field equations, which we are hopefully going to talk about it. And then everything is going to be more clear at this point. So this is the end of the 5th session.